welcome, and good evening, good morning, from whichever part of the world you are from. My name is Raj. I am an assistant professor at TU Delft working on signal processing challenges for multi-agent systems. You are here at the ASI webinar series, which is Autonomous Systems Initiative webinar series run by the Signal Processing Society. It's an initiative for online seminars from leading academic and industry experts on signal processing. Uh, we talk about a variety of topics, including network autonomous systems, human-machine interaction, situational awareness, and the inference and signal processing challenges broadly speaking. So today we have an industry expert, John from Toyota Research Institute, who will be talking about uncertainty-aware modeling and control for driving at limits of handling. We're very excited to have you, John. To all the audience, let's keep the questions to the end of the talk, if possible. The floor is yours, John.
Great. Thank you for the introduction, Raj. My name is John Subosits, and today I'll be talking about our approach to uncertainty-aware modeling and control for driving at the limits of handling. This work includes contributions from the entire Extreme Performance Intelligent Control team at Toyota Research Institute, but I'd like to especially recognize the work of Frank Jamu and Thomas Lev in the following. Let me begin by just saying a very few brief words about Toyota Research Institute and the work of the Human Interactive Driving Division. So Toyota Research Institute is organized into 5 broad divisions. These include energy and materials, human-centric AI, robotics, and large behavior models. My team works within human interactive driving, which has the goal of building new AI-driven technologies and tools that amplify human capabilities to create a truly intelligent vehicle experience. Ultimately, our goal in doing this is to make driving safer and more fun. So you can imagine that a future intelligent vehicle could support you in emergencies, helping you avoid collisions whenever physically possible, but it could also make driving more fun. So taking some of the mundane aspects out of it, making it feel safer or more enjoyable, just generally less stressful. In order to do this, we focus on 3 broad research pillars. So the first is driver vehicle performance and safety, where we use challenge problems to push the limits of autonomy with the goal of ultimately building expert skills into autonomous vehicles. The second goal is to better understand people or drivers using data-driven techniques to understand how they behave and how they react in challenging situations. Ultimately, the goal is to combine these expert-level driving skills in the autonomy with our understanding of human drivers into shared autonomy systems that could perform as well or better than either human or autonomous systems alone. Today, I'm going to speak about the first of these, how we use challenge problems like racing and drifting to build expert-level driving skills. So drifting, for those of you who are not familiar with it, means operating the vehicle in a state of controlled oversteer. So as you can see in the picture, the vehicle, in this case, a Toyota Supra, is pointed directly at the obstacle that's been placed on the track in front of it. However, as you can tell from the skid marks, the vehicle is actually tracing a smooth arc around it. So this kind of extreme nose-in attitude in the corner is oversteer and is is a trademark of drifting. Now this next video will make drifting a little bit more clear for those of you who aren't familiar with it.
Going autonomous.
Temporarily giving an ordinary driver
Whenever you're ready.
the drifting skills of an expert.
Great run.
Okay, so why should we study drifting as a challenge problem? Well, simply put, drifting is a challenging skill for even experienced human drivers. You need to be able to stabilize the vehicle in equilibrium and transient maneuvers that are dynamically unstable. So you always need to be making corrections to the steering, throttle, in order to keep the vehicle sliding, but not spinning out. And despite this challenge, skilled human drivers are able to do this with great precision. So placing the vehicle precisely where they wish while maintaining the stability. So basically, by tackling autonomous drifting, we've kind of forced ourselves to develop expert level driving skills within AI. We can then apply these capabilities to scenarios that are more commonly experienced in everyday driving. So for example, avoiding sudden obstacles, handling adverse conditions like snow and ice, or potentially teaching driving skills to enthusiasts. So you could imagine your car is a skilled driver and could teach you and coach you as you work to master some of these skills on your own. Okay, so now that we've kind of covered the context and the motivation for the work, let's start to look at some of the technical aspects. So most state-of-the-art approaches in vehicle control at the limits leverage model predictive control. Model predictive control requires three components. The first is a forward model of the vehicle dynamics. So basically, typically this is a system of ODEs that predicts the evolution of vehicle state in response to certain control inputs from your current state. You need a cost function, which describes the desired behavior of the vehicle, and some sort of optimization algorithm that allows the autonomy to reason about the control inputs that it'll make now and over some prediction horizon in order to best achieve these objectives. We like model predictive control as an approach because you can keep your model the same, but you can change the behavior of the vehicle through your cost function. So on the left here, you can see the prediction horizon of the vehicle in a racing and obstacle avoidance task. So as the obstacle appears as the yellow dot, the vehicle is able to smoothly replan. And then once it's past the obstacle, it goes back to racing. However, it doesn't need to really do any switching. This is all simply encoded by the cost function, which has a given objective and then obstacle avoidance constraints. Similarly, we can take the same model predictive control approach that we used for racing and obstacle avoidance and apply it to drifting. So here on the right, you see a different vehicle drifting a figure-8 trajectory. And here, the emphasis is more on trajectory tracking. All right, so as we saw in the opening video, these approaches can work quite well in practice. However, there are a number of open challenges. These tasks remain challenging because they are both highly dynamic and require operating the vehicle in an unstable regime. However, we know from studying the best human drivers that they can reliably operate near the limits, even in unseen scenarios. And they can automatically improve with experience. So the two questions for us are, how can we capture some of this behavior that human drivers do so well and capture that directly in the autonomy? And so the two approaches we're looking at currently are uncertainty-aware control and learning-based control. All right. So the first component of this is the search for robust performance. And here we've chosen to account for uncertainty directly in the control design as one mechanism for dealing with this. Instead of modeling the vehicle as a system of ordinary differential equations, we're now using sets of stochastic differential equations. So for those of you who are not familiar, stochastic differential equations, actually, sure, I'm not sure if you can see my cursor, but basically
Your cursor is visible, John. Yes.
Okay, perfect. Thank you, Raj. So stochastic differential equations include two components. The first is a drift term, not to be confused with drifting. That basically encodes kind of the deterministic behavior of the system. And then also a diffusion term, which is kind of a random disturbance that's applied to the process. Right. We like this formulation because it builds on the nominal dynamics that you use in standard MPC with these random disturbances. But perhaps more interesting for us is that we can actually capture, in some frameworks at least, uncertain parameters. So the main one for us is the friction coefficient between the tires and the road. So here we've denoted that mu. And for example, you could think of it as distributed with some normal distribution. Now, the idea being that if you simulate this ODE forward for a given set of control inputs from a given initial state, kind of as shown in this rough sketch at the bottom here, your trajectories would evolve as kind of through some envelope, right? And if your goal was to avoid the obstacles that you see here as pink ellipses, you might want to say that, with high probability or near certainty, I would like all of my trajectories out in the future to avoid these obstacles. Okay. So beyond this uncertainty-aware control, kind of balancing risk and reward, we also want to be able to adapt online. So as we get more data about how the vehicle is responding in a certain context, we would like to be able to adjust our models and reduce the uncertainty. So if you have some initial distribution over friction, as you drive, this uncertainty should reduce. You should become more certain about the vehicle's dynamics. And this, at least in high performance situations, should allow you to get closer to the vehicle's absolute limits and ultimately improve performance. Okay, so today I'm going to cover three aspects of the work from the group. The first two sections of the talk will focus on stochastic modeling, so how we actually capture these the dynamics through stochastic differential equations. And then the third piece will be the use of these models in uncertainty-aware planning and control. All right, let's begin with neural SDEs. So one desirable property, perhaps, as you kind of learn from data, you would like your model to be certain where you have good experience, but perhaps less sure where you have yet to see data from the vehicle. So ultimately, our goal is to predict distribution over the system trajectories. So illustrated here, imagine you have some ground truth data for the vehicle's response in state space, shown in black. But you only have measurements from certain portions of the state space, here shown as blue dots. Ideally, what you would like your model to learn is that where you're near your observed data, you should have relatively high certainty. So your model in red or its predictions should be relatively sure. You should be able to describe the evolution of the vehicle state very accurately. However, when you're far from observed data, the uncertainty should be comparatively large, right? Because I'm not really sure how my vehicle will respond yet. So how do we do this in practice using neural SDEs? So the neural SDE framework that we use is much like the standard stochastic differential equation model that I described earlier. However, both terms are parameterized by neural networks. So beginning with the drift term, we can leverage some of our knowledge of vehicle dynamics in order to ensure that we do this in a data-efficient way that generalizes fairly well. So I guess to begin with some elementary vehicle dynamics, I guess most of the important forces for describing the planar motion of the vehicle come from the tire forces. So here we've shown these as the lumped longitudinal force at the front axle, FXF, the lateral force, FYF, and similarly for the rear axle. Then, because we have good knowledge of the vehicle's geometry, we can say how these tire forces affect the dynamics of the vehicle. So basically, if we know the steer angle and the wheelbase, for example, and we know how these forces effectively act on the body. So because we know these things exactly, we can focus our learning on the parts that we don't know. And this, for us, is typically the tire response. While there are models that characterize this fairly well in the literature, you can always become more precise through the use of data. In parallel to this, we want to learn a kind of a distance-aware uncertainty estimate for the diffusion term. So like I said before, where we're near our data, we want to have high certainty, and then farther away, we want our predictions to be, or our measure of the certainty of the predictions to be relatively less sure. And so this is also represented as a neural network that encodes, in some sense, like a distance metric. There are some, to actually learn this from the data, what we try to do is, where exactly at the observed data points, this uncertainty should be small, and it should be a local minima. And then as you get farther and away from the data, basically this term should go up to some maximum that we've chosen. So once we combine these two components, we now have a model that we can forward simulate to get potentially sample trajectories for any given control input sequence. So that's shown here at the top right. In certain places, the dynamics are relatively stable along the trajectory, so your uncertainty collapses. In other places, it's high, so you have a divergence in the trajectories. All right, so now that we've seen a little bit about the neural SDE framework in the abstract, let's talk about how we apply this specifically to the problem of car control for drifting. So looking at the right half of the slide, we focus on using the neural SDE framework to capture the evolution of the velocity states. So these are the yaw rate R, the total velocity V, the side slip beta, and the wheel speed omega. The evolution of what we call the kinematic states, so the position and angle of the vehicle, its pose, these we can get simply from kinematics, so we don't need to learn these from data. For the problem of drifting control, our two main control inputs are steering and throttle. During drift tests, our primary objectives are to track a reference trajectory that, while following most closely its side slip profile. In order to do this, in order to leverage some of the uncertainty, we first sample from the distribution. So basically the stochastic process that describes your SDE, we can sample from it each time we solve this problem. So 2-3 times like this. And then in expectation, we can minimize the cost along the trajectory over our prediction horizon. Plus potentially a learned cost to go in our terminal state. So this would say, this would be useful for, say, staying close to the path and dealing with the limited length of your prediction horizon, say. Okay, when we actually run this on the car, it's performed quite well. We've been able to learn vehicle models with very limited amounts of data, so as little as 3 minutes of manually driven characterization data for the vehicle. And when used for control, it's improved the tracking accuracy of the drift controller pretty well. So you see overall on the left, kind of a top-down view as well as an in-cabin view. You can see that it's able to drive quite smoothly, suggesting that has relatively good prediction or anticipation of the vehicle's dynamics. And then looking at the overhead map on the right, you can see that the tracking accuracy using the neural SDE approach has improved over a hand-engineered bicycle or single-track model with more traditional empirical models for the vehicles or the tire force generation. Okay, so I've introduced the neural SDE framework, which allows us to learn from data, and it allows us to capture some notion of uncertainty. However, these models ultimately are fixed. So once you learn to characterize the vehicle's dynamics, you could do some online updates, but they're not necessarily designed for that. Whereas human drivers are very good at leveraging previous experience and adapting very quickly to sudden changes in their environment. So, for example, if you were to cross onto a wet road, you've driven on a wet road before, and you're able to leverage that information very effectively. So in this next section of the talk, I'll talk about how we've used diffusion models to do something similar. Now, the questions that kind of motivated this research were this desire to capture the whole distribution of vehicle dynamics, and then how we could exploit that distribution for control and adapt quickly online. Now, maybe the key insight or the insight that we're trying to leverage here is that the vehicle performance or the way it responds to control inputs is in some sense multimodal, meaning that there's a few distinct modes that we're trying to capture. So for example, this could be the vehicle responds a certain way on dry asphalt, on wet asphalt, and on snow and ice. And so obviously there will be some noise or variation depending on the exact tires that are on the vehicle, various setup parameters, the exact surface condition. But the key idea here is that generally we expect it to be a certain number of almost distinct modes, and we'd like to capture or identify those at least approximately in an efficient way. However, most modeling techniques that are used in uncertainty-aware control focus on fitting a single weight average approach. So the stochastic differential equation model that we saw, if we model it as driven by some sort of white noise process, this is zero mean, and certainly very unimodal, right? So every time we predict a sequence of trajectories going forward, you would expect, at least over short term, you would have a single mode. However, looking at some of the recent advances in diffusion models, we know that these are very good at representing multimodal distributions. So with this kind of background in mind, with these motivations, with these tools that recently became available, we started to look at ways of using diffusion models to represent the vehicle dynamics. However, diffusion models can be relatively slow to predict. They're maybe not as data efficient to train. It's not clear how you could necessarily leverage some of the physics information we know about vehicles in order to learn more effectively or to ensure that you generalize better. So how can we kind of reconcile these two needs? So the approach we ultimately came up with was kind of a two-step approach. Here, starting at the top, as the vehicle is running, you can look at your recent experience, so how the vehicle has responded over, say, the past 3 or 4 seconds. You can then condition the diffusion model on this and use this to generate a possible set of candidate parameters here denoted by theta at a relatively low frequency, so something that you can achieve with a diffusion model. These parameters theta are then the representation of your vehicle dynamics that we can use within our existing MPC framework based on the neural SDE approach that I described in the previous section. So basically, you can think of this as parameter estimation and its use in control. Importantly here, though, we're able to separate this to kind of 2 timescales. So we're able to continue to do the very fast control that we need to do with MPC. So for drifting, typically you need to be able to solve these problems at least 20 times a second in order to maintain control of the vehicle. So certainly this is faster than you could probably do reliably with the diffusion model directly. However, we can update our belief about how the vehicle will respond at a lower cadence using the diffusion model. All right, let me explain a little bit more about how this works in practice. So the goal here is ultimately to have a single model that you can use in model predictive control for performance driving in over a broad distribution of environments. So you could imagine deploying this directly to multiple vehicles or applying this to multiple surface types with vastly different friction coefficients, such as wet roads or dry roads. Right. So as I kind of started to get into on the past slide, what we want to do is basically leverage the diffusion model to augment our existing neural SDE framework, effectively generating the sequence or a sequence over time of parameters that well describe the vehicle's behavior. So here, these parameters theta can be a relatively high dimensional vector. So this could include things like inertias of the drivetrain, but more importantly, it's capturing neural network weights that ultimately describe the tire forces. So here, I think this is ultimately what's kind of motivated the look at diffusion models as a estimation mechanism versus more traditional estimation techniques, is the fact that we're operating in a very high, but potentially, or in practice, seemingly quite correlated space. All right. So ultimately, at each time step, every time we solve an MPC, we can use a single mode from these drawn from the distribution predicted by the diffusion. However, in future work, we'd like to look at sampling multiple modes simultaneously, so effectively leveraging the full distribution, allowing us to, perhaps put some likelihood on different conditions. So, for example, putting perhaps some belief that the road is wet and simultaneously like some belief the road is dry. So currently we're able to consider both these possible. While we have some understanding of both of these possibilities, we're only considering one at a time. And to be clear, these are not explicitly programmed. These are rather kind of learned from the data. And I'll talk a little bit about how we do that now. All right, so how do we actually train and implement this algorithm? So we work in kind of two steps. One is the offline training of the diffusion model itself, and the second is its online deployment on the vehicle. So first, using our existing fitting process for the neural SDE, we can take an existing offline data set of vehicle trajectories. We can sample these over some short horizon of a couple seconds, and then we can fit neural SDE models that well approximate the vehicle behavior. Then, using a standard diffusion model training process, we corrupt these with Gaussian noise and train simultaneously a diffusion model to denoise these. So given enough time, we can do this slowly offline and ultimately build a diffusion model that can go from white noise, denoise it through a sequence of steps, and ultimately arrive at a set of neural network parameters and associated physical parameters of the vehicle that well represent the data on which it was conditioned. It is, in fact, this kind of iterative process that makes the diffusion model slower than, say, than we would be able to use for model predictive control. All right. Then when we actually look at the online deployment, we've fixed the diffusion model, so we're not actively training either model online. However, as the vehicle drives, we can take the past several seconds of vehicle trajectory, use this as conditioning for our denoising model. Then, as quickly as is useful, so in this case, about twice a second, we can start from a random initial guess of the vehicle's parameters, denoise this, and then use the ultimately denoised parameters, which should well approximate the vehicle's dynamics in MPC. So here we'll look at kind of, I've argued to you that the distribution is ultimately multimodal. Here we'll see kind of a little, maybe a high level evidence that this might be the case. and that there is value in adapting your parameter estimates from experience. So here you'll see kind of the posterior distribution of two physically meaningful parameters predicted by the diffusion model. These are not the only ones, but on the left, you see the inertia of the drivetrain, and on the right, an estimate of effectively what's the tire force coefficient, so the max rear force. You can see that when we're driving along a grip trajectory, so when the vehicle is not sliding, we kind of retain this bimodal distribution. So the model isn't necessarily sure about the vehicle's parameters. However, as the vehicle is pushed to its limits and actually made to slide, you can see that the uncertainty in the represented parameters basically collapses into a unimodal distribution. And so, as you might expect, as you push the vehicle to its limits, you get a better idea of how it responds, and you're comparatively sure about the vehicle's parameters. So this is exactly the behavior we were hoping for, and suggests that our initial assumptions about vehicles and their parameters seem to be borne out at least a little bit in the data. Okay, so how well does this actually work in practice for control? So what you're seeing here is top-down views of a number of different drift trajectories driven by two different autonomous vehicles. Importantly, we are in fact using the same diffusion model. So not the same diffusion modeling framework, but actually the same diffusion model to control both these vehicles across all these different trajectories. So basically, as the vehicle is driving, it's learning to infer which of the two it's dealing with, or two vehicles on three different models of tires with different friction coefficients and different dynamic response. And then, it's identifying the model sufficiently well that we can use this effectively in MPC. So this was really quite kind of a striking and surprising result for us. I don't know that really anybody in the vehicle control community that focuses on limit driving techniques has been able to see such broadly applicable approaches to their hardware. So we were pretty pleased with this, but this was also kind of the extent of what we could do testing at our proving grounds in California. So typically the weather is dry here. We have two test vehicles. But we were also interested in testing in very different conditions, right? So how could you handle rain, for example? Because I use that as a motivating example. Typically, when driving on wet asphalt, your friction coefficient is about 20% lower than on dry asphalt. So a significant reduction, and one that requires pretty drastic changes to your control inputs in order to stabilize the vehicle safely. So luckily we were able to get access to a wet skid pad to do this. So here the diffusion model was trained not just on dry data like it had been for these demonstrations, but also augmented with about 5 minutes of wet driving data. So the diffusion model is able to think or have experience with both dry asphalt and wet asphalt across both of these two vehicles. And so deployed in this context, it was also actually able to drift, and you'll see a video of this test here. So as the vehicle kind of rolls onto the wet asphalt, you'll see a little bit of initial understeer, but as the diffusion model gains enough experience, it's able to adjust its parameters appropriately, and the vehicle ultimately goes into a stable drift. So this next video will show that exact same test, but from inside the vehicle. So you can see kind of the operation of the autonomous controller. Two things, or maybe the thing I will most highlight for you, is the general smoothness of the steering and the relatively consistent engine note. So the vehicle is able to kind of hone in very nicely on the equilibrium, and it's able to control it there and deal with the instability very effectively. Here, the vehicle is tracking a desired circular trajectory, actually turning to the right with its wheel turned to the left, and just kind of tracking a nice stable drift. All right, so far we've seen how we can capture uncertainty in our models, how we can adapt effectively online using prior experience, and actually have relatively good performance over quite broad range of conditions. However, what I haven't talked too much about yet is how we actually incorporate state constraints, or how we might start moving towards that, because obstacle avoidance is one of our motivating challenges. So, how can we think not just about stabilization and tracking problems like we did in drifting, but actually use this framework to look to slightly more challenging motion planning problems, such as trajectory planning or obstacle avoidance. And so let's think a little bit about how we can couple the state constraints, relevant state constraints, with the approach that we've started to describe today. As kind of an initial motivation for that, I'd like to kind of share some simulation results of drifting with state constraints. So here, the pink area is an area you should avoid. When your model is perfect, so on the left, you have kind of a deterministic MPC view of the world. You're able to track your desired path exactly. And it's not really an issue that your keep out area is so close to your desired trajectory. However, when there's uncertainty in the model, so particularly around the tire friction, you need to be a little bit more conservative. So if you need to stay away from the inside edge of the track, for example, you might leave a little bit of buffer, drift a little bit farther away from your desired trajectory, basically incur some penalty in terms of your cost function, in order to ensure that with high probability, you don't have a constraint violation. Now, these examples from drifting, I think, illustrate the need for this relatively well. However, we're going to change our focus a little bit here and look away from drifting towards racing. So racing has, I guess, the advantage that when formulated as a minimum time problem, you tend to push up against your constraints very often, right? So in order to find the fastest way through the corner, you're typically turning in from the very outside edge of the track, reaching an apex at the inner edge of the track, and then kind of tracking out to the outer edge again. And you're doing this whole thing while operating as near as you can manage to the absolute friction limit of the tires. So in drifting, you operate kind of in the sliding friction regime of the tires. In racing, you want to maximize the tire force throughout. All right. So the main objective in what we would call a racing problem is ultimately completing the course in minimum time. However, at the same time, you need to stay on the track, and you can formulate your MPC problem kind of as follows, right? So minimize time, and we can kind of get away with minimizing time directly if we can discretize the dynamics of the vehicle in space. And then you can apply some regularization in terms of, say, keeping close to a desired trajectory. And then as standard in MPC, you want to satisfy your dynamics. You have to plan from your initial state, and you need to observe your input and state constraints. All right, so does deterministic MPC work? You might think that based on our previous good drift results, it might. This is actually a harder problem in the sense that you can build up yaw rate beyond what you can stabilize on wet asphalt. So here, what you're seeing is, let me play that again. As the vehicle actually transitions from the dry asphalt to the wet patch, you can see here on the dark side on the right half of the screen. As soon as the front tires leave that wet patch, the vehicle goes into extreme oversteer. And because we're modeling the vehicle as operating on high friction, dry asphalt, it does not take sufficient corrective action and ultimately spins out. So like I said, this is actually a harder scenario probably than we saw in drifting previously because we don't have a consistently wet patch. Rather, we have a sudden transition from high friction to low friction. So you're able to place the vehicle in states that are not easily sustained on the low friction surface. So fundamentally, the challenge here is the same one that I've kind of emphasized throughout, is that the dynamics model is inaccurate. And in particular, for vehicle dynamics, this primarily comes down to a misestimation of the tire forces. So the estimate is very good when you're operating on dry asphalt, where it's where the model is close to correct. However, as you transition to wet, suddenly you expect a sustaining or stabilizing moment from your rear tires that you simply don't realize. Now, in the past, there's been a number of engineering ways to kind of deal with this, to make this easier to work with in practice and just mitigate the challenges here. So, various approaches to conservative control or risk-averse control. Sometimes they use constraint padding approaches. So for example, you could bring your road edges in, allowing more runoff area should the vehicle deviate from the desired trajectory. The question here is, how do you know how much? Is this something that you should tune manually, or is this something you should be able to get from at least approximately from a certain procedure? However, bringing the road edges in also has the additional benefit in that it forces you to drive slower because you're driving on a tighter radius, forcing you to slow down for any given model of the vehicle's dynamics. So here we've kind of adjusted the reference trajectory to X tilde, which is more conservative, so slower. You could go beyond this. You could further regularize the system by using a stronger feedback relative to a desired trajectory, so de-emphasizing the minimum time aspect of the problem. You could further keep the vehicle away from challenging states, so limiting the total velocity of the vehicle, say. Or you could more directly aim to keep the vehicle away from its friction limits, so by limiting the slip angle of the tires, alpha, say, or penalizing the magnitude or constraining the magnitude of the tire force use. None of these solutions, while they can be made to work in practice, are particularly satisfying because ultimately what they do is they force you to look away from the goal that you're ultimately trying to achieve, which is, getting around the course as quickly as possible, and which ultimately forces you to push up against the friction limits of the tires. So what can we do about this? Well, the standard MPC formulation uses one vehicle dynamics model. So this could be, or maybe in the case of the initial stochastic ODE, perhaps a few separate instances of it, or But instead, what if we were able to reason about several possible futures with relatively high uncertainty over the vehicle's parameters themselves? So here in the middle, we have a standard tire force curve. So what this shows is that as the slip angle builds of the tire, as it has some lateral velocity, it generates a restoring force. So a lateral force that kind of aims to keep that's exerted back on the vehicle. Now, ultimately, this friction force is limited by the tire road interface, and you have ranges of friction coefficients, anywhere from about 1 on dry asphalt down to, maybe all the way down to 0.7 or 0.8 on wet asphalt. So here you'll see kind of a family of curves that correspond to these different conditions. And the question here is, what if you were able to reason over multiple different tire models on the front axle, the rear axle, so the different oversteer and understeer balance, for example. I guess for those of you not, familiar with vehicle dynamics, understeer would just limit understeer at least would be when the front tires reach their friction limits before the rear, and oversteer would be the reverse, with the rears ultimately reaching their limits first, putting you at risk for a spin. Okay, so we would love to be able to reason about multiple different possibilities, different tire force responses, and perhaps compute a trajectory that minimizes our cost function in expectation, right? So if we were able to sample, say, m equals 10 different tire models, each have their own set of tire parameters theta, could we solve for each of these 10 possible futures one common control input u, so that we could apply to all of these different vehicles that would ultimately achieve our objective and ensure that each of the 10 possible trajectories that we're reasoning about observes our desired constraints. So all 10 possible future trajectories should stay on the track, and in aggregate or on average, they should minimize our objective. So kind of a stochastic optimization problem, as it were. So the main challenge with this for real-time implementation is that, while we had to work to solve the initial MPC problem, or do some work at least to solve that sufficiently fast and over sufficiently long horizons to make it useful, we now have a significantly bigger MPC problem to solve. And this might, in practice, this would be prohibitive for real-time implementation. So to kind of get around this, we're leveraging the parallel structure of the different rollouts or the different models that we're using in this MPC approach. So we kind of use a two-stage approach. So for each of the 10 different trajectories, I guess let me take a step back and first emphasize that we're solving this through sequential quadratic programming. So at each time step, at each iteration of the solver, we're computing a simpler local approximation to the problem, and then we're taking a step in the direction that should reduce the objective value. So due to the nice parallel structure of the problem, the fact that we can predict each of these dynamics independently, we can parallelize this on the GPU, leveraging JAX, and we can make these compute these approximate problems very, very quickly. Then the QP solve itself can then be done on the CPU, and this overall system is faster than using purely the GPU or purely the CPU. So using this setup, we can ultimately plan at 20 hertz, even reasoning over 10 different models, without having to resort to any sort of approximation or anything like that. So how well does this work in practice? Let's return to our original motivating example that showed the limitations of deterministic NPC when your model is very wrong. And then on the right, we'll see this, this multi-model approach. Play that one more time. So overall, you can see that the vehicles ultimately have pretty similar velocities around the track. You know, the risk-averse approach is not being markedly slower through the corners. However, when you hit a patch of water, because you've put you started to account for what might happen if friction were comparatively low, you ultimately have vastly different behavior in practice. All right. So looking at the data from those two videos, we see that ultimately you slow down very, very slightly, maybe about a meter per second or so over the entire course. And you make very subtle changes to your control inputs, right? So the steering angles are relatively the same. You pick up the throttle in roughly the same place, but to a lower level. The braking is also adjusted a little bit in order to ensure that you have stability through the brake zone and that you don't get too sideways entering the corner. So what you should take away from this is that when driving at the limits, relatively subtle changes in your control inputs can have very, very different outcomes, and that reasoning over even extremely different vehicle models can result in these relatively subtle changes to your control inputs. All right, to kind of summarize this section of the talk, we like racing as a motivating example because it forces us to push up against the constraints. It's very sensitive to estimates of friction However, using this parallel approach and combining this into a single optimization problem, we are still able to reason about possible different sets of vehicle dynamics at a sufficiently high frequency to do real-time control. And as we've seen through experiment, this does pay dividends in terms of robustness when your conditions do not match your nominal dynamics. All right, to wrap up my talk, today we've seen kind of three sections, how we've used neural SDEs to capture uncertainty about the vehicle dynamics, how we've used diffusion models to adapt the parameters of the neural SDEs very rapidly online, while ensuring that these parameters are ultimately something similar to what describes the vehicle dynamics well. And then finally, how we've used different possible sets of vehicle parameters. So here illustrated in a case with various friction conditions to reason about uncertainty to ensure that we can respect our constraints with high probability, even when we have great uncertainty about the vehicle dynamics. So to summarize the entire talk, the message I really want you to take away today is that by coupling uncertainty-aware models of the system dynamics with optimal control approaches that can leverage these representations of uncertainty, we're able to improve the ability of intelligent vehicles to drive safely, even up to their absolute performance limit. I guess with that, I'll end my section of the talk and turn it back over to Raj and I guess to the audience for questions.